Hi, welcome everyone. I'm Lotte and I will do this presentation on behalf of Tech United together with Koen. We want to show you our planning towards RoboCup 2016. These are three main points we are focusing on this year. Starting with replacing our Kinect cameras, all of our robots, field players and goalkeeper now uses the first Kinect. We aim to replace them with Kinect 2. Secondly, I will move on with shooting at goal, improve the efficiency on goal, and finally improve the gameplay to make it faster. Now,
thanks. Welcome. I will present something about the Kinect 2, as Lotte just said. Does this work? No, switch it on. Ah. Okay. So currently we are using the Kinect version 1, so the Kinect of the Microsoft gaming thing, Xbox indeed. And we use it on to see balls, so not to observe obstacles or detect obstacles, but only to see the high balls. We have mounted the Kinect on each robot, and we have actually mounted two on the goalkeeper to have a wider view angle. But there are some shortcomings on this Kinect. And the first one is that the CCD has quite a low sensitivity, which means that if there's a lot of light, we can set the exposure to a low value, and we can get images up to 30 Hz. But normally when we play in championships, the light conditions are not that good, and we need to set the exposure to a little bit higher value, and we can't run at 30 Hz anymore, and we get less images. Another issue is that the CCD has bad colors, or bad quality colors, so the color level is not that good, which means that calibration of the ball is more work and is less stable. So that means that sometimes when you calibrate just before a match, that during the match the light condition slightly changes and the color, the color is also, the color calibration is also degraded, which means that it's more difficult to see the balls during the complete match. We have some stability problems, mainly in the connectivity, which means that, for example, we cannot start up one of the streams, or during the game it's losing connection. And the depth range is limited to 6 meters, so I heard higher numbers from, I guess it was Minho. But we can see balls up to 6 meters. And that is not so far, because if the ball is moving at a high speed, or 10 meters per second, for example, like when we do a full shot, or when water is shooting at our keeper, the ball will have a speed of about 10 meters per second, and that means that we only have 0.6 seconds to actually react after the first feature that we see. So that's why we start moving to the new Kinect. So there's a new Kinect camera, Kinect 2. It has a high quality CCD, so it's more sensitive, so we think that we can always run at 30 Hz, so we don't have to downscale it anymore. We have a better color quality, so the color images are much better, which makes it much easier to calibrate, so maybe calibrate only once during a tournament. We hope that we have less stability issues, that connectivity is better. We did some experiments, and we can adjust the depth range to see balls up to 9 meters. So that's the complete the complete half. So that should be sufficient. And we have an increased view angle. So maybe we can replace the two Kinects on the goalkeeper by only one, or at least each robot has a better view angle, or we mount it on the robot. One drawback of the Kinect 2 is that it has a different way of capturing the depth images, which means that you require a GPU to process the images. So before we could process everything on our own CPU, so on the computer of the robot. But now we have to switch to a GPU, and our robot in the robot is a back of industrial PC, and it doesn't have a GPU, and it doesn't have extension possibilities for a GPU. Yeah, there is you can add a big bracket on it and put a GPU, but that's not sufficient, or that's not what we want. So we are looking at something else, and that's a Jetson TK1 development board. That's a development board which has an NVIDIA chip on it, so an NVIDIA GPU. And these are the specs. So it has an NVIDIA Kepler GPU with the 192 CUDA cores, and it also has an ARM Cortex on it. So we have, I think actually we have 2 or 3 ARM cores which are close to the connected to the GPU. So we can run, for example, 4 cores. Okay, so that means that we can run Linux on this board and use the GPU to offload the image processing, and we can program it using CUDA, so that the image processing is programmed by means of a parallel language. The connectivity it has a USB 3.0 connector for the Kinect, and it has a gigabit Ethernet LAN that we want to use to connect to the robot. So how do we want to detect the ball? So first of all, we want to do registration of depth and color image. That means that we are mapping each pixel in the image. We map the depth image onto the color image, or the other way around. So what we do, we have to remove the distortion of the lens, which you have in your color image, and then you can map each pixel so that you have, for each pixel you have depth info and color info. Then we use color segmentation, use the Google annotated database. So in the database, all the colors are defined. So if you say, I want to have all yellow pixels, then it makes a map which says, okay, these pixels are considered yellow by Google. And that works pretty well with the new Kinect. The next, we do a flood fill algorithm for blob detection. And then we select the blob based on the size and distance ratio and the width and height ratio. So we know the size of the ball, it's circular. So we know the ratio, and we know the ratio. And when it's further away, the size in the image gets smaller. And the last step, we do the transformation to the robot's coordinates. A little bit about the implementation that we have at this moment. So we have the GPU. The GPU is doing the JPEG decompression of the color stream, and it's doing the depth reconstruction from the infrared phase images towards the real depth picture. So the Kinect 2 has a time of flight principle for making the depth image, and that's what we run at the GPU, and also the flood fill on the GPU. And at the moment, at the CPU, we're doing the registration, so the mapping of the color and the depth pixels, and we want to move that to the GPU using a CUDA. And the color segmentation is also in the CPU, mainly because it's working fine, so we don't need to move it to the GPU. And the blob selection is also running at the CPU. The results so far, that we were able to detect the ball at 30 Hz. And the accuracy is still unknown because we did measurements with the Kinect, but we didn't have a second sensor as a second source to validate the measurements. And I have a movie of it. You see here the red box which annotates the ball. And when you move the ball around, you see that it's capable of tracking the ball quite good. So this is a standard yellow ball that we also use during tournaments.
Some Portuguese coffee, right?
Sorry?
Yes, some Portuguese coffee.
I'll show it again. No? I won't? No, so what we do, we capture an image, and then we try to couple the depth info to the color. And if we don't have depth info, we remove the pixel actually. Then we do blob detection, so we look for yellow blobs. And then we use the depth information to see how big the blob should be if it's considered to be a ball. I'll show it one more time. So on the top left you can see the distance with respect to the camera, how far the ball is from the Kinect. So not 9 meters yet, but yeah, to 4 meters it's working quite well. So some future work. What we did for the Kinect version 1, we implemented the tilt compensation. So the Kinects are not mounted very sturdy on the robots, which means that they can, if there's a collision with the ball, that it might move a little. So that's why we use compensation. And how that works, the Kinect is also looking at the field, so it tries to fit the plane, which is considered to be the field, and with respect to that plane, it can compensate how it's looking forward. So what we need to do, we should move that implementation to the Kinect 2. And besides using it for ball detection, we also want to use it to detect obstacles. So far we use it mainly on a keeper, and there the main priority was to see balls. But of course, it's also a very nice sensor to use for obstacle detection. So that's the next step. We want to remove the field from the registered image, and everything that's left is actually or the ball or an obstacle, which then can be an opponent or a peer, but that's handled by the world model. So then we get more information from Kinect 2 than just balls. And in the far future, we also want to do some line detection and also the goal detection. So instead of what we do right now, we check where we are, and then we know where the goal is, and then we are going to shoot at the goal. But we might think that we get some more accurate shots if we actually look at the goal. So look where the goal is. So if it's moved slightly to the left or to the right, that we can actually shoot in the goal instead of shooting at the position where the goal is supposed to be. One more slide about communication with the Jetson that I think is nice to tell. So as you probably all know, is that we use the Kambara communication with RTDB to communicate between the robots. So how does it work? We have an RTDB database on the robot, and here we have our 3 executables or processes which are running. And they all share information with each other through this database. And then we have another process, which is the COM process. And the COM process is reading the records which are marked shared in the database and sending it over Wi-Fi to the other robots. And that's also what we want to use inside the robot itself. So we have the Jetson board, which is connected through LAN, local area network, to the robot. And we want to use a second COM process on the robot PC, and also a COM process on the Jetson board, and then communicate through that COM. Let the 2 RTDB databases communicate with each other. Because we think that's a flexible inter-process communication. It's easily extendable, so you can share information from the robot to the Jetson board and vice versa. So if the Jetson board needs, for example, the position on the field, so where the robot is, it can also get that. Well, this we can easily do with the RTDB and the communication as it is right now. So we only have to adapt the COM slightly, that it also works on that you can select a second Ethernet connection or a second IP address. And what we are thinking about, maybe possible performance or reliability improvements, is that instead of sharing all information to the Jetson board, because we can mark the records either local or shared, which means that all the information which is also for the other robots is now also sent to the Jetson board. So we think about adding a new record which might be called remote or something like that, so we can send only a subset of the records to the Jetson board. Another improvement might be to use TCP/IP instead of UDP if we think that that's better to communicate, to get it more reliable, or to make this communication process triggered instead of fixed rate. So at the moment we run this communication at 40 Hz. That means that all robots communicate at 40 Hz at a fixed rate. But maybe on a Jetson board it's much more interesting to actually trigger the COM to send data to the robot when it just acquired a new image and get the balls, and then just sending the data directly instead of waiting for a new cycle to end for the communication. So far about the Kinect 2. Are there any questions already, or shall we just proceed with the second part? Yeah? Yeah?
How do you choose the seed for the
Sorry?
How do you choose the seed?
Ooh, that's I don't know.
Second question, please. How do you validate the ball? Just for the size relationship, or do you use information from the depth to validate information?
Well, we calculate the size that it should have based on the distance. So we check how far it is away, and then we know what the distance it should have in the image. So that's one thing. And another a rule that we use is the ratio between the width and the height. So it should be circular. So those 2 steps are currently used to to say whether it's a ball or not.
Do you remember Brazil?
I remember Brazil, yeah.
You remember the venue that has those yellow things on the top of the building?
Yeah, yeah.
So that led us to a solution for this kind of problem based also on the depth information.
Okay.
I strongly suggest you to take a look. We had a paper this year in Robotica.
Okay. Good.
Because this is really a problem, it was also for us. My third question is related to the black information that you have on robots for obstacle detection. I think that should be also a problem. So I would like to see a result also for that. At least with the Kinect version 1, you cannot distinguish, for example, the black information from the robots.
Okay, yeah. I think it worked on our robots, but I can imagine that many other robots it won't work so well. That's true. We are still in the first step, so we are using it now for ball detection. But indeed, we know that but maybe the new Kinect with the new way of making depth images. So instead of structured lights, it uses time of flight. So maybe you get better results with that. But yeah, we didn't investigate that so far.
Okay, thank you very much.
Okay. Yeah.
I have a question about latency. Do you have any figure about latency from the real ball movement until you get the information into the CPU?
No, we didn't measure that yet. But I think because the Kinect is quite fast, it's not that significant. And something else, it's not a big issue. So with what we see is that it is fast, and that might be enough. Because what we do, we use it mainly for checking the direction of the ball. So if we see the ball is flying through the air, the only thing that we are interested in is what's the direction, so that the goalkeeper can stand over there. And it's not interested when it actually hits the goalkeeper. It's just that the goalkeeper should go there as fast as possible to make sure to block the goal. So it's different than intercepting a pass, for example. Then you might want to have more information when the ball is where. But here it's sufficient to know where it enters the goal.
Did you give a rough number, like 100 milliseconds? Or?
No, I can't.
I'm not up to date with the Kinect. Is there an open source driver for it?
It's I think the LibFreeNect has a new version, which supports the new Kinect, and that's also actually why we need to go to a GPU. So I think the water team is running it on the CPU because they can run Windows. So there is a Windows driver available, and I think with the Windows driver you are capable of running it on the CPU. Okay. But with the LibFreeNect you can run it on a. You need the GPU to get it working.
And GPU means NVIDIA and not Intel integrated graphic card?
Just a GPU is fine. So the processing power of a CPU is not sufficient.
Okay.
So if you can run it on a FPGA, it's probably also fine. But
sounds like you would have problem with an Intel integrated graphic card.
No, but the integrated graphics card inside our industrial PC is very weak, so you can't actually use it to program to process images. It's because you also need something to offload your image to that video card, of course.
Now the problem with the Kinect is the influence of light. So if you have lots of lighting, it doesn't work that much. Is it still true with the Kinect 2? Have you tried with different lighting, or it works? Do you still get the 9 meters, or does it reduce with lighting?
We didn't make it very difficult for it. So we used different light conditions, but still it was always inside. So still like in an office. We didn't check with extremes, so we didn't make it very dark or very bright. But everything seems to be better than the Kinect 1, and especially with the depth image is much sharper. That you could see that the resolution seems better, less noisy. So it is better, but numbers how good, I don't know. Yeah.
Okay. Any other questions? Let's move on.
Yes? Stuart? Okay. Okay, I will move on with improving our efficiency with shots on goal. So after the last RoboCup 2015, we evaluated our final matches, semi-final and final, and we came to the conclusion that we had a lot of goal attempts, but few of them were successful. In the semi-final 29%, and even in the final 7% successful goal attempts. So there is some improvement possible there, and we made an analysis of the kind of shots on goal, what the cause was, why didn't they end up in a goal, and these were the solutions. Well, mainly the first one, improve the lob shots, and the second one is what we already were working on, presented it during the scientific challenge, and I shortly want to show you how far we are or what we're doing now. Yes, but first improving the lob shots. Our current lob shots are mostly used to pass over an opponent at goal, but most of the times it's a weak shot at goal. We are using a shooting lever, which can be used at many different shooting angles, but we are now currently only using 3. One for just a pass, simple pass, one for shooting straight at goal, and one for the lob shot, so the maximum shooting angle of 45 degrees. And this results, yes, in a low velocity, so a weak shot at goal, and we want to improve this, and our goal is an accurate lob shot with an adjustable shooting angle, so that the robot can choose which shooting angle is the best for a nice shot on goal. And this is how we did this. So we had a ball model, we already had that, but validated it for a bouncing ball. And after that, we determined a relation between the ball trajectory, so where the ball ends up for this bouncing ball for a lob shot, and the lever setting, so the shooting angle, but also the initial velocity. And finally, inverse this problem, and from a desired target, get the initial conditions for the lever settings for this shot. So first a short movie. Some of you already saw it during RoboCup. We have a ball model. This is a bouncing ball shot by a robot, and the red line, and now the blue, the green line. So this is our ball model, which is pretty accurate. And this is what we used. And then we did experiments. So we had all our robots shooting shots at goal using different settings for, well, in this case K and L. K is our kick effort, so the duty cycle we send to the PWM module, so for the shooting velocity, and L, the lever settings, so the angle of the shooting lever. And we got all of these kind of graphs where we have a ball trajectory. And in this way we had a relation between this ball trajectory and these lever settings. And so the final step was to inverse this problem. And this is the result. And here we use this green board in the goal with 2 holes. And those holes are our desired targets. So we want the ball to enter that hole at the highest point, so with the highest possible velocity. And from different spots on the field, the robot shoots the ball. So we have 2 examples from this side. And you can imagine that such a desired target is the upper right corner of the upper left corner of the goal, and dependent on the position of the opponent you want to pass over and your position on the field, you can now calculate the perfect settings. And we hope to increase our efficiency with this. Well, then the shooting with effect. For those who didn't join RoboCup, I have this movie of a project one of our graduation students is working on, and the goal is to shoot with effect, so to give a certain spin to the ball, and when the ball bounces on the ground, the direction of the ball changes, so like this, and the ball is spinning in the air, and now it's, so this is an animation, we're not there yet, but this is what we have for a goal. And this is how, so he first made that a ball model estimation, like I showed before, and he inverts this problem. So now, and this is already how far he got. So he has, for a desired target, he knows what initial inputs, which parameters he should adjust for this. And now he's working on the 3rd bullet point, which means that he's investigating with different experiments how we can add spin to this ball. So in what ways you can do it. Well, our ball handling uses small wheels. You can use those wheels to give a certain spin to the ball, but also using the position of the shooting lever. So not shooting ball off center, so shooting, hitting the ball off center. And he's now investigating, he just started with that. So I unfortunately don't have nice movies or pictures of that, but we will certainly share them if we are this far. But hopefully the goal is in Germany, hopefully we can show we can show this to everyone. Okay, then the final point we are focusing on is the faster gameplay, and this is related to our strategy implementation. We're now working with different roles, and those roles have certain tasks or actions they can perform, but not each role can perform every action. So, for example, a defender catches the ball because he's defending an area. He gets the ball, but he's not able to make a pass to an attacker which is far in front. But instead of that, they switch roles. The defender becomes an attacker, and he goes to the opponent's field side to make an attacker of it, to make an attack. And at the same time, the attacker becomes a defender, so goes back to our own half to be a defender. So you get those role switches, and you see that this happening on the field, and it's not very efficient. So those are the limitations. The actions are limited per role, and that's not what we want. And the state is not preserved during role switching. So when he goes to a new, when the defender becomes an attacker, it gets a new role and it starts all over. So this is how we want to implement it. No behavior implemented in roles, so each role should be able to do every action, and the only roles we end up with is 2 defenders, 2 attackers, so the robots are nicely spread over the field in a smart way. But if the defender gets the ball, he can immediately pass the ball to an attacker on the other side of the field, so we have a faster gameplay. And we can implement sequences of actions, so the defender can really think of, okay, I play the ball to the attacker, and the next thing I'm going to do is also go to the other side of the field for a free spot to so he's in a scoring position, for example. So these sequences were not able before because of those role switches, and you had to start over all over again when you switched from role. So these improvements will enable this, and we are aiming to play in this way next tournament. And that tournament will be in the Netherlands. So this is a promotion slide. We organized the European Open in the end of March, beginning of April. Hopefully you can all manage to be there. A nice tournament to practice. It will be in Eindhoven. I'm part of the organization committee, so if you have any questions about it, then please ask. Thank you for your attention. I'll put this on. Any questions?
Yeah, that's the question.
Yeah.
Okay, lots of new stuff that we're hoping to see in maybe Dutch Open first,
Yes.
and then in Germany, hopefully. And so let's hear from the other teams. Questions?
Okay, so my question is regarding your behavior switching and role switching. I don't think it's a good idea to have global actions or behaviors, as you call, or action. You call them actions, right?
Yeah, an action like dribble, passing.
Okay, so high-level behaviors. Because sometimes, at least in our case, there are dependencies between actions, and those dependencies are related to the role. And you can have, for example, one action like dribble, for example, but you want to make different dribbles on different roles, for example. And if you are going towards a solution where you have every type or any type of behavior or action, you will end up with a huge list of actions to do. Or you have a simple list, but you don't have that configurability. What I'm asking is, have you considered any kind of relation between actions inside a role? Are those configurable? Yes, no?
I think Koen can better answer that question.
It's not necessarily that each role can execute any action, and it can be that it's not said that an action has not parameters which depend on the role or position on the field. So of course, you can provide information to the action, which is dependent on what kind of role the robot has, where he is on the field. Indeed, maybe he doesn't want to dribble so far if he's a defender or an attacker because he should shoot at goal. And I don't know. Yeah, we don't know whether that's really role dependent or maybe more position dependent on the field. But it is configurable.
Yes, my concern is that when you change the same instance of that action on
on different roles, you are influencing one role with another one. That's my concern, but just a comment.
Yeah, that might be a need, yeah. Thanks.
More questions?
Regarding the efficiency of the kick to the goal, how did you manage to deal with the velocity of the robot? Because you provide experimental results showing the kick to those holes, but when the robot was stopped. What is the effect of the robot movement in that procedure? And you managed to estimate correctly the velocity of the robot and use that information to perform a better kick?
So if I understand it right, you mean the movies I showed, the robot was standing still, and what happens if the robot is moving and then adding a kick. In this project, it wasn't taken into account, so the robot was standing still, but now someone is working on indeed the dynamic lob, so if the robot is moving. So I can't tell you right now what
I'm just asking because you said in those topics that was green, that one of the things that you took into consideration was the initial velocity. So that is why I'm asking how you do it and how good is that estimation?
So yeah, what we now only did is what with the still standing robot. So we didn't deal yet with the driving robot and then shooting.
Thank you.
Although Koen wants to say something about it.
We do have conversation when the robot is shooting with a flat shot at the goal, but not for the new lob shot. What we do, we take into account the robot velocity. So, for example, if he's driving sidewards, we take the initial velocity of the ball, which is moving along with the robot. We take that into account. And for example, if we move to the right, then we aim slightly to the left, that the ball end up at the correct position in the goal. But that's something we already had in Istanbul, I think. So that's not new.
Sorry. Still regarding that improving lob shot, do you have any results regarding the repeatability of what you can get? Because I remember you said that regarding those two holes,
Yes.
The idea was to shoot on the top of it.
Yes.
The second one, for instance, enters on the hole, but on the bottom of it. So my question is, what is the level of repeatability that you can get from your estimation, basically? Because balls aren't round. So you may get a real nice model of the ball, but the actual ball won't be exactly that one. So do you have any results on that?
Well, for the experiments of the movies I showed, there were two examples, but the student did those repeatedly. And for example, 9 out of 10 were into the holes, like.
Okay. Did you try to reduce the size of the holes?
Not that far yet, but as I said, we want to use this to shoot very accurate in the goal, and that's what we're now working on. So implement that in.
Your hope is that your level of accuracy in terms when playing against water will increase significantly, right?
Yes.
Any more questions regarding any of the 3 teams that were presented by Tech United? Oh, okay. Thank you so much again.